Welcome. In this video we're going to take a look at how we can use derivatives to give us information about one-dimensional motion. We're going to be able to take a position function and take the derivative of it to get the velocity function, take the derivative of that to get the acceleration function, even maybe take the derivative of that to get the jerk function, should we want that. Jerk being the change in acceleration over time, believe it or not. So here we've got a function. Let's say it's graphing the vertical position of an object at any time t, and the function is graphed for us, and we have negative 1/4 t squared plus 4 being the equation for it. Now we know already that the slope of a tangent line gives us the velocity on this graph, the slope of position versus time, the rate of change of position versus time. Okay, so if I want to find out, like for instance, what the velocity of this object is at 3 seconds, then I can draw in that tangent line and I could ballpark the slope, but the derivative can give us the slope at that point exactly. And it will give us then the velocity of that point exactly. So first we got to take the derivative here. So we're going to take the derivative of y with respect to t. And this is going to give us the velocity function. The derivative of the position with respect to time is the velocity at any time t. We're going to use the power rule to take the derivative here. So 2 times negative 1/4 is negative 1/2. The exponent goes down by 1, so that's t to the first, and the derivative of any constant term is 0. So here we have the function that will actually give us the velocity of the ball at any time t. So what is the velocity at, not 4, how about v? What is the velocity at 3 seconds? We just have to plug that in to the function that we just derived. So it's negative 1/2 times 3. So we'd be looking at negative 3/2 meter per second, and I'm going to correct a mistake that I see here. I don't know why I said the unit for time was meters per second. No, it's seconds. So we've got then a velocity at time 3 is going to be negative 3/2 meters per second. All right, and looking at the graph, that totally jives with the blue tangent line that I drew right here. It's negative, and we could probably do some rise over run and ballpark that at negative 1.5. So now we can take it a step further. We've got our velocity function. Let's go ahead and graph it. It's a linear function. It's got a y-intercept of 0, and it's got a slope of negative 1/2. So that, for better or worse, is our velocity function. And now, remember, the slope of velocity is the acceleration. The rate of change with respect to time of velocity is the acceleration here. We can see that the acceleration is negative. Taking the derivative of the velocity function, dv dt, will give me the acceleration function at any time t. All right, so what is the derivative up here? It's again t to the first, so using the power rule, 1 times negative 1/2 is negative 1/2 t to the 0, which is just negative 1/2. Oh yeah, right, the acceleration is constant. That velocity function is linear. Okay, so we have a constant negative acceleration of 1/2 meter per second squared here. Okay, so when given the position function, take the derivative once, you've got the velocity function. Take the derivative twice, you've got the acceleration function. All right, now this we could have dealt with using kinematic equations. Why? Because the kinematic equations apply when acceleration is constant. Okay, the real usefulness comes in when we're dealing with non-constant accelerations. So let's take a look at an example of that. So here we have a horizontal position given by a cubic function. It's not immediately obvious to most folks that this is a non-constant acceleration, but if you take the derivative of t cubed twice, you're going to end up with a function that's got a t in it. So our acceleration is going to depend on time. It's not going to be constant. So first, I just want to say that with that function right there, if I ask you what is the position of the object at time 4, you're going to plug in 4 and tell me where it is. If I'm going to ask you when is the object at the origin, you're going to plug in 0 for the position, and you're going to solve for t. I'd probably use a graphing calculator at that point. All right, so this allows us to describe some of the motion of the object. We take the derivative of that, dx dt, is going to give us the velocity function. So using the power rule, it's 3 times 3, which is 9t. The 3 goes down by 1, so we have t squared. And then we have 2 times negative 8, which is going to give us negative 16. And again, the exponent goes down by 1. 2 minus 1 is t to the first. And then the derivative of any constant is 0. So this then is the velocity function. If I ask you what is the velocity at 4 seconds, you're going to plug in 4. If I ask you what is the velocity at 20 seconds, you're going to plug in 20. If I ask you at what time or times is the velocity 0, you're going to plug in 0 here and solve for t. One of them is going to be 0, right? So this, again, is a powerful tool for us to figure out how fast the ball is moving at any time t. This one up here tells us where the ball is at any time t. Okay, and take it again a step further. Second derivative of position with respect to time is also the first derivative of velocity with respect to time. That's going to give us the acceleration at any time t. So again, using the power rule, 2 times 9 is 18. 18t to the first minus, this is 16t to the first up here. 1 times 16 is going to be 16. All right, so here we have a linear function that gives us the acceleration. Is the acceleration constant? No, it depends on t. Okay, the acceleration at time 0 is negative 16. The acceleration at time 1 is going to be, arithmetic, 2 meters per second squared. So our acceleration is changing as time marches on. So what do we do with this? You can give me the acceleration of the object at any time t. What's the acceleration at 5 seconds? Plug in 5. When is the acceleration going to be 0? You're going to plug in 0 for the acceleration. Let's do it really quick. 0 is equal to 18t minus 16. We're going to add 16 to both sides and divide by 18. And oh boy, simplifying that, what do we got? 8/9 of a second. So when the time is just less than 1 second, we're looking at the acceleration being momentarily 0. All right. So now with these 3 functions to describe the motion of the object, then we have a complete picture. Okay. I can give you the position, velocity, and acceleration at any time t. All right. I could give you the average velocity between 1 and 10 seconds. Don't use the velocity function, use the position function. Okay? If I ask for the average acceleration between 0 and 3 seconds, you're not going to use the acceleration function, but you're going to use the velocity function. Let me show you why. So here are some very rough sketches of the velocity and acceleration functions. Our velocity is a parabola, opens upward. Our acceleration is linear. And if we wanted to, I was asking you in the previous one, what if we want to find the average acceleration from something like 0 to 2 seconds? You got to remember that the slope of velocity versus time is acceleration. And if we want the average acceleration, let's say from 0 to 2 seconds, then we're going to find the velocity at 0, we need to find the velocity at 2, and we need to find the slope of that line to get the average acceleration. All right, so that requires you to use the velocity function. You're going to need to take the final velocity, or the velocity at 2, so v at 2, minus the velocity at 0, and then you're going to have to divide that by the time interval, which is 2 seconds. Okay? So the acceleration function isn't going to help us out in finding the average acceleration. That's kind of weird. Similarly, if I wanted to find the average velocity between 0 and 2 seconds, you're going to have to go back and use the position function to do that. All right? So basically everything that we have done up to this point, finding average velocities, average accelerations, finding out where something is, how fast it's going, what the acceleration is, we've been using kinematics for constant accelerations. Now we can use just simple calculus, derivatives, to get our 3 equations of motion, and this is going to work for non-constant accelerations too. So it's very powerful. All right. So there it is. That's all I got for you now. See you next time.